This is part 3 of the lecture on general relativity. At the end of part 2, I went through the first 2 tests of general relativity that occurred after the publication of the theory in 1916. Now, specifically the second test, which occurred during the solar eclipse of 1919. That test is an example of what is called a gravitational lens. I provide for you in the screencasts that accompany these lectures a few other examples of gravitational lenses. Make sure that you watch those screencasts in addition to these lectures. Now here in part 3 of this lecture and beyond, I'm going to start to give you a number of other examples of the curvature of the geometry of space and time. Before I do, however, I want to tell you a little story about Albert Einstein. Somewhere along the way, you may have heard some crazy rumor that somehow Einstein was bad at math, like he flunked a high school algebra class or something like that. That's entirely incorrect. Instead, let me tell you the real story. As Einstein was developing the hypothesis of general relativity, what he realized that he had to do was take a 4-dimensional geometry and then curve it in the presence of mass. Now, back in the 19th century, the mathematician Riemann worked out the mathematics of a 4-dimensional geometry. So what Einstein realized that he had to do was he had to take Riemann's mathematics of a 4-dimensional geometry and curve it in the presence of mass. That's difficult to do. So then therefore Einstein enlisted the aid of a mathematician friend of his. This mathematician named David Hilbert was an expert in Riemann's geometry. And so essentially what Hilbert did was he assisted Einstein basically in applying his hypothesis to this 4-dimensional geometry at the end of Einstein's process of developing the theory of general relativity. Hilbert himself actually saw in his own derivations of his mathematics the Einstein field equation about a week or so before Einstein himself actually derived it. So because Hilbert did play a role in the development of the theory in the latter portion of the process, a portion of the theory is named in his honor. Sometimes hyperspace is referred to as Hilbert space for that reason. That's the real story behind Einstein and math. Einstein was not a mathematician, he was a physicist, so he basically enlisted the aid of an expert in Riemann's geometry at the end of this process. Okay, now how can you actually begin to visualize exactly what is meant by hyperspace, this 4th spatial dimension? And then moreover, how can you picture it as being curved in some manner? Well, the Mechanical Universe episode, the Lorentz transformation, provides for us a clue. Towards the latter half of that episode, the episode does a very good job of constructing what are referred to as space-time diagrams. I'm going to go ahead and draw one out for you here. Okay, what we do is we take 3-dimensional space around us and we refer to it as a 2-dimensional plane. So it's a 2D version, if you will, of 3-dimensional space, say like so. All right, so here's a plane. This right here is a 2D version of 3-dimensional space. Now in 3-dimensional space, you have 3 axes, x, y, and z, and they're all perpendicular to each other. Now imagine a 4th spatial dimension that is perpendicular to x, y, and z. On this diagram, that would be a dimension in this direction, like so, perpendicular to the 2-dimensional plane. In the Mechanical Universe episode, they just refer to this dimension here as time. Specifically, however, what we do is we take the speed of light c and we multiply it by time t. When we do, we end up with a 4th spatial dimension, hyperspace, that is perpendicular to the other 3. This is what is referred to as Hilbert space. The presence of the Earth's mass curves this 4th spatial dimension. This dimension is curved by the Earth's mass. So consider a projectile. Consider, for example, the baseball, like so. Now, in the Newtonian picture of gravity, the force of gravity is exerted upon the baseball, causing it to accelerate downwards at 9.8 meters per second squared. However, in the Einsteinian picture, the baseball is actually just obeying the law of inertia. It's moving in a straight line at a constant speed the whole time, but it's moving through curved space. Now, how could you even possibly begin to visualize this? Well, what I want you to do right now is pause this lecture and then look at the video in today's folder called the Space-Time Stretcher. It's a specific demonstration that was built by an engineer that shows the curvature here of hyperspace by the presence of the Earth's mass. Go ahead and watch that video now. Okay, now that you've watched that video, now we can begin to understand, for example, on a space-time diagram, how this spatial axis here is curved by the presence of the Earth's mass, and that then causes the motion of a projectile as we see it, for example, here at the surface of the Earth. Okay, let me give you some other examples here of curved space. Okay, other examples of curved space. Okay, let me give you now, in a general relativistic manner, exactly what is meant by a black hole. Okay, as I mentioned, Einstein published general relativity in early 1916. A couple of months later, a mathematician named Karl Schwarzschild found a specific solution to the Einstein field equation. The Einstein field equation is a partial differential equation. This mathematician named Schwarzschild found a specific solution to that equation. The specific solution to the equation predicts the geometry of an object that is described in the following way. Okay, now go back to my original demonstration here from part 1 of today's lecture. So we have, for example, here the felt that represents two-dimensional space, and then the presence of the baseball here curves that two-dimensional space into a third spatial dimension, forming a gravity well. Basically, the depth, if you will, of the gravity well is determined by a couple of things. It's determined by the mass of the object, it's determined by its size, and it's also determined by its density. Karl Schwarzschild found a solution to the Einstein field equation that predicts the following geometry. Okay, so let's say that right here is the two-dimensional surface of the felt, and now I'm going to go ahead and curve it into a third spatial dimension, like so. If you have an object that has a finite mass, but is literally of zero size, in other words, it's a geometrical point in space, this then means that it has an infinite density. An object with an infinite density would create a gravity well that is infinitely deep. Okay, that infinitely deep gravity well, at the bottom of it, if you will, is this point in space literally of zero size, but of finite mass. Therefore, it has an infinite density. At the bottom of this infinitely deep gravity well is what is called a singularity. Okay, now, Karl Schwarzschild, just a couple of months after Einstein published general relativity, wrote up his solution describing this geometry here in a paper. He published the paper, he sent a copy to Albert Einstein. Einstein literally refuses to believe his own theory. Einstein thought that it was absurd that the universe, for example, could contrive such a monster, as he referred to it as. So Einstein develops this beautiful theory that describes gravity as the curvature of the geometry of space and time. Schwarzschild comes around and says, look, your theory predicts the existence of such an object, and Einstein literally refuses to believe his own theory. However, we do see objects, of course, today, like the supermassive black hole, for example, at the center of the Milky Way galaxy, that can't be explained any other way. What we have found about general relativity is that general relativity makes some wild mathematical prediction about nature. Nobody believes the prediction, and then we find things in nature that can't be explained any other way. Black holes is the prime example of this. Okay, now, what would you see if you could somehow approach a black hole and look at it? Would you see a well that kind of like disappears, if you will, into nothingness in this manner as I've drawn here on the board? No. Instead, what you would see as the opening, if you will, is a sphere. You approached a black hole, you would see a perfectly featureless black sphere. That perfectly featureless black sphere is actually not an object. It's instead a horizon. It's referred to as the event horizon. In honors physics and in AP physics, back in chapter 8, I went through a specific example, a specific description of what is meant by the event horizon. But why would it look spherical? That's what I'm going to concentrate on here. The reason why it looks spherical is because what you're actually looking at is a four-dimensional object, but you're looking at it in three-dimensional space. Now, how can you wrap your head around exactly what is being described there? Well, in the early 20th century, a short story was written, and this short story is referred to as Flatland. Some of you may have heard of this short story before. It's only about 20 pages long or so. It turns out that the story of Flatland provides for us a nice allegory, if you will, of how you could begin to visualize a four-dimensional object. Let me give you a description of that. Okay, the story of Flatland is as follows. The characters in Flatland, they inhabit a two-dimensional universe. It's just a plane. The main character, by the way, in the story is named A Square. So let's say right here is Flatland. It's a two-dimensional universe. And then the characters in the story live in this plane. Now, over the course of the story, the characters in Flatland become aware that their universe contains more spatial dimensions, specifically a third spatial dimension, even though they cannot directly experience it. Here's then how they realize that they are living in a three-dimensional universe. Over the course of the story, a three-dimensional sphere passes through Flatland. So, for example, let's say that perpendicular to the two-dimensional universe of Flatland, like so, is a third spatial dimension. And then let me go ahead and right here draw a sphere, like so. And that sphere, we'll say, is moving in this direction. Okay, and then right here is the character in Flatland. As I said earlier, the character's name is A Square. A Square observes the sphere passing through Flatland. And as he observes it, he realizes that what he is seeing is a three-dimensional object in his two-dimensional space. So what would the sphere look like as it passes through Flatland? Can you visualize this for yourselves before I tell you? Well, the characters here in Flatland would see the following. At the moment that the sphere begins to intersect Flatland, then the people in Flatland would see a point. And then what they would see is they would see that point expand outwards as a circle in their two-dimensional space. At the point where the circle is of its largest value, this would then correspond to the little equator, if you will, that I drew right here for the sphere, basically intersecting Flatland. It would look, for example, say something like this. Let me see if I can more or less draw this. Kind of looks like so. Once again, here's that third spatial dimension like so, and the sphere is moving in this direction. Here's A Square. Notice from A Square's perspective, in his two-dimensional space, he would see the sphere as it passes through Flatland go from a point to expanding outwards as a circle, the circle would have its maximum diameter at the moment that I've drawn here when the equator of the sphere is passing through flatland. And then that circle would go back down to a point as the remainder of the sphere passes through flatland. So then therefore A square realizes that he in fact does live in a three-dimensional universe, even though he cannot directly experience that third spatial dimension. So when we look at the event horizon of a black hole, the reason why it appears spherical, in other words, it looks three-dimensional, is because you're looking at a four-dimensional object in our three spatial dimensions. This is how general relativity begins to describe a black hole. Okay, now how many of you have seen the film Interstellar? Okay, Interstellar does a pretty good job of illustrating some of the effects of general relativity. It does make a few mistakes, but it does get a couple of things right. For example, there are a number of special effects in the film where they actually show a black hole in the distance away from the characters. And in fact, what does it look like? It looks like a sphere. The first radio map image of the supermassive black hole at the center of M87, we made that radio image, remember, from observations last year. I've showed you that radio image in class. It also appears in my screencast that accompanies this lecture. Well, what does the event horizon of that supermassive black hole look like? It is, in fact, a sphere. Now, getting back to the film Interstellar, by the way, there's one more effect associated with black holes that they depict very nicely in Interstellar, and they do, in fact, get this correct. What is referred to as gravitational time dilation. There's a sequence in the film, a series of scenes where basically the following happens. The characters approach the black hole in their spaceship. And then two of the characters leave the spaceship and they go down to a planet that is in orbit around the black hole, very deep in the gravity well. In other words, if we go back to my original diagram here, of the black hole's geometry, here's where that planet was in the film. So now this is specifically in the film Interstellar. Okay, so here is the two-dimensional plane, and then here's the infinitely deep gravity well like so. Okay, down here we'll say very deep in the gravity well like so. This down here was the planet in orbit around the singularity. Okay, and then you've got the starship here, for example, like so, with the characters approaching the black hole. And then two of the characters leave the starship and they go down to the planet here that's in orbit around the singularity, very deep in the gravity well. Over the course of those scenes, the characters who go down to the planet only experience a short amount of time, literally just a few minutes. However, decades goes by for the character that remains here on the starship. This is correct. This is an example of what is called gravitational time dilation. Here's how gravitational time dilation works. Imagine that the character down here on the planet takes a light, and that character then shines that light up to the person that is over here. As that light progresses from this character to this character, it moves at the same speed. The speed of light is the same for all observers in all reference frames, but it's moving through curved space. Specifically, the geometry of space here, close to the singularity, is much more curved than it is over here, further away from the singularity. The greater curvature associated with the space here stretches out the light. It causes it to have a large redshift. So imagine, for example, that the light is being emitted like so, but it gets more and more stretched out as it progresses and then eventually reaches the person here. The light is redshifted. This means that it has a longer wavelength. So if it has a longer wavelength, this then means that it has a larger period. Imagine that the period of the light is like ticks on a clock. So as the light is emitted, the people here see the light, for example, with its normal color, and so then therefore they simply see tick, tick, tick associated with the period of the light. But as the light gets stretched out, as it's propagating towards this character here on the starship, It's propagating through curved space as it propagates, and then therefore, because it gets stretched out, the period gets longer. So let's say at the period of the light, for example, that the characters emit right here, the light that actually comes from their flashlight, let's say that the period is just 1 second. So then therefore there's 1 second, if you will, in between ticks. By the time it gets to here, however, because the light has been stretched out, then the period we'll say is longer. Specifically, we'll say it's 2 seconds. So then therefore, for every second of time that elapsed for the characters here on the planet, 2 seconds of time elapsed for the character here on the starship. That's correct. This is a gravitational redshift. It's gravitational time dilation. They do get it correct in the film. Let me go ahead and pause this here. This is part 3 of today's lectures.